Hi and Assalamualaikum. We are from Group 5. Before we started, I would like to introduce our group members. Okay, this is our team. Nur Airina Zahira, Nur Fazrina, Nur Kristina Rose, Nur Alia Kasara, and Nur Adriana. Hi, I will present our list of content for the presentation. First, we will start with our group names and members' names. Then, we will continue with the problem statement. After that, we will show the filler table. Next, we will present the result and calculation, which include part A, part B, and part C. Then, we will move on to the discussion section. Finally, we will end our presentation with the conclusion. Hi, my name is Nur Kristina Rose binti Erasmi. Today I will explain about the problem statement. Today I will explain how we can model pistol root expansion and know when it became unsafe. A pistol root is a part of a machine that moves back and forth. When the machine is used many times, the root can become longer because of heat and pressure. This is called expansion. If the root grows too much, it can cause friction, misalignment, or even damage the machine. Engineers need to predict this growth so they can plan maintenance and prevent accident. One way to model expansion is by assuming the root grows by the same amounts every time. This is simple and shows steady, predictable growth. Another way is to assume the root grows by a percentage of its current length. In this case, the expansion gets faster over time because each new leg is slightly longer than the previous one. The root became unsafe when it reached the maximum leg it can handle. By tracking its growth, engineers can know when to repair or replace it. In conclusion, understand how a root expands, whether stability or faster over time, help prevent machine failure and keeps operations safe and reliable.
Which help us organize our problem and approach systematically. FILA stands for Facts, Ideas, Learning Issues, and Action Plan. First, for the facts section, from the problem we know that the piston has an initial extension of A1 mm at cycle n equal to 1. We also know that thermal expansion causes the rod to expand every cycle. However, there is a maximum safe length m, and if the piston exceeds this length, it may cause engine failure. Lastly, different parameters such as A1, D, R, and M are assigned to each group. Next, the idea section. To model the expansion, we propose using two mathematical approaches. If the expansion increases by a constant amount each cycle, we can use an arithmetic sequence. If the expansion grows proportionally, we can model it using geometric sequence. We then plan to compare both models to see which one reached the safety limit and faster. To make the comparison clear, we will use digital tool like Excel to visualize the result. Moving on to the learning issues, there are several things we need to clarify. First, we need to identify the exact formulas for both arithmetic and geometric sequence. Then we need to learn how to solve the cycle number n when the piston length reaches m. We also want to understand how heat affects the material and contribution to expansion. Finally, we need to learn how to create a comparison graph using digital tools. Lastly, the action plan. To address these issues, we will refer to books and websites for the sequence formula. We will use online tutorials to help with calculations and Excel function. After that, we will analyze our result and discuss our finding as a group. If needed, we will also refer to guide videos or the help function in Excel or Word. In conclusion, this pillar table helps us break down the problem clearly and guide us step by step.
Moving to part A, we analyze the piston root's thermal expansion using an arithmetic sequence model. We assume that a constant growth of 1.0 mm per cycle from an initial length of 99.5 mm. By applying the n-term formula shown on the slide, we determine that by the 15th cycle, the rod expands to exactly 113.5 mm, while our sum formula calculation shows a total cumulative extension of 1,597.5 mm. over that duration. The most critical part of our result involves the safety limit, which is 114. It is confirmed that the road remains safe through the 15th cycle, but it officially becomes unsafe at the cycle 16. The most critical part of our results involve the 114.0mm of safety limit, and our data confirms that the road remains safe through the 15th cycle, but it officially became unsafe at cycle 16, reaching 114.5mm. As you can see from our linear graph in this slide, this graph provides a steady and predictable growth rate, which is essential for engineering because it allows us to forecast the exact moment the component becomes unsafe for operation. This will ensure maintenance happens before a failure occurs. Okay, that's all from me. Then I will pass it to my teammate for further explanation. Thank you.
This study analyzed the expansion of a piston roadway to increasing temperatures using arithmetic and geometric sequence models. For Group 5, the interior road length is 99.5 mm with constant arithmetic increase of 1.0 mm per cycle and a geometric growth ratio of 1.010. The maximum safe road length is 114.0 mm. The arithmetic model predicts a linear growth where the road length increases by a fixed amount each cycle. In contrast, the geometric model predicts exponential growth, where the increase becomes large over time due to compound effect. From the TNVS and graph, the geometric model reached the maximum safe length earlier, cycle 15 compared to arithmetic model cycle 16, indicating a higher safety risk. The SNVSN graph show that cumulative extension increased more rapidly in the geometric model than in the arithmetic model. In conclusion, the geometric model provides a more conservative and realistic prediction for long-term safety analysis, while the arithmetic model is suitable for short-term approximation. The arithmetic model predicts a linear increase in piston road length, while the geometric model predicts exponential growth. From the Tn versus N graph, the geometric model reached the maximum safe length of 114 mm at cycle 15 earlier, and the arithmetic model reached it at cycle 16. The Sn versus N graph show that cumulative extension increased more rapidly for the geometric model due to compounding effect. This indicates that the geometric model is more sensitive to prolonged temperature increase and provides a more conservative safety prediction. Therefore, the geometric model is more suitable for long-term safety analysis, while the arithmetic model is appropriate for short-term linear approximation.
Arithmetic sequence menunjukkan constant linear expansion pada piston rod bagi setiap cycle. Geometric sequence pula menunjukkan accelerating expansion, di mana pertambahan panjang meningkat dengan lebih cepat pada setiap cycle. Geometric model pula meramalkan keadaan tidak selamat, unsafe condition, dengan lebih awal kerana kesan pengumpulan haba. Thermal expansion berlaku apabila peningkatan suhu menyebabkan greater atomic vibration dalam haba. Tahap expansion dipengaruhi oleh temperature, material properties and juga cooling condition. This study demonstrates that arithmetic and geometric sequence can be used to model the expansion of a piston rod during repeated 80 cycles. The arithmetic sequence show a steady and linear increase in road length, manakala geometric sequence represent a faster and accelerating expansion.
The comparison revealed that the geometric model predict unsafe condition yearly, menjadikannya lebih sensitif to continuous heat exposure. This clearly show how different mathematical model and significant effect safety prediction. Overall, the result highlight the impact of temperature on material expansion dan menunjukkan bagaimana mathematic sequence help to simplify and analysis real-world engineering problem. This project also demonstrate the importance of mathematics in understand thermal effect and supporting safe engineering decision.